Let's begin. Welcome again. I'd like you to put your name tags, please, in front of you, just so that I can try to continue remembering your names. We'll have your group names printed out, hopefully, by Thursday. Last week, we left on a rather not happy note with iterative solvers, and it felt like everybody got lost with the discussion on iterative solvers. But I want to tell you that the discussion on iterative solvers is more of a, here's what's out there. It's what's next, what's coming next, not necessarily to hold you strongly accountable on iterative solvers. But you need to be knowledgeable of the basic idea of iterative solvers, which is essentially to start with a guess and refine that guess based on the governing equations. Now, there was a paradigm shift that we did when we looked at the Jacobi iterative solver, and that was, hey, we solve equation 1 for unknown 1, equation 2 for unknown 2, and so on. What do you do with the other unknowns? You just start with a guess, and then take the new estimate, treat that as a guess, and rinse and repeat. And I think that's a critical paradigm shift in your thinking about how most numerical methods work. This procedure is called an iterative procedure. It starts with a guess and refines the guess. We will see it today as well with nonlinear solvers, which is impossible to do without using that idea. And another idea that was introduced with iterative solvers is this thought of how do you calculate an error when you have multiple or many values to track. If you remember the Taylor series, when we computed the sine or the cosine, we tracked one value, right? It was just that value of sine x, and the more terms we added, we were able to track these successive approximations, the approximate error between iteration k and iteration, or term k and k plus 1, take the difference, divide by the more accurate value. But that was a single value. With many values, which value do you choose? And I introduced the idea, reminded you of the idea of the vector norm, which if you treat each variable, the solution to each variable, as one value in a vector, then you can track the relative approximate error for each one of those values, like I showed here in this table. And then you can together treat them as one vector and take the magnitude of that vector. That's one norm we call the L2 norm or the Pythagorean norm. But you can also say, I'm going to take the worst case scenario, the variable that is converging the slowest. So for example, in these three values over here, one of them has an error, let's say 10 to the minus 9 here. The other is 10 to the minus 9. This first one has an error 10 to the minus 7. There's 2 orders of magnitude difference between this error and this one and that one. So you'll say, hey, I'm going to hold this, the worst case scenario, accountable for convergence. Okay, so that's called the L infinity norm. You take the maximum value of the error in that vector, the maximum value in that vector. Okay? That is an important idea when you are trying to measure error in a system where variables are related to each other. Like, which one do you hold accountable for the system to say that you converged? It doesn't matter which norm you choose, L infinity, L2, L1, L3. There's like all sorts of measures of this error vector, but as long as you choose one and you're clear about it. Now, the nice thing about linear systems, okay, so we get an approximate solution with the iterative solver. Remember, with the direct solver, you get an exact solution. So if you were to take your answer and plug it back in the governing equation, so remember, you had ax equal right-hand side. You're solving for that vector x. If you were to take that solution and plug it in x, multiply it by a, you're going to get b, exactly b, plus round of error. Okay? With iterative solvers, that's not the case, but the linear system, the governing system, is a great way to assess error as well. although you don't have an analytical solution, but you have a set of governing equations that will allow you to check if your solution is close enough or not. So, for example, you can simply take your kth iteration, xk, and plug it back into your linear system of equations. So you have ax equal b. You have 2x equal 3. So we know x is 3 over 2, right? So you plug the value that you compute. Let's say you got 1.3. You plug it back and see, is this equal to 3? No. Continue iterating until you satisfy ax equal b. So in a way, you have an exact solution, right? You have a measure of whether your solution is close to the exact one or not. So you could do that, or you could do this approximate error. If you know the exact solution, you could do the, when you're doing verification, you could do your iterative solution xk minus the exact solution, or you could do this approximate error that I showed in the previous slide. So from iteration to iteration, from iteration to iteration. I really like that measure because it's independent of the linear system that you're dealing with, and you can just simply track the best that your computer can do. Because my computer might be able to achieve convergence faster than your computer. I might have a larger chip and a faster chip. I might be crunching numbers faster than one other computer, right? And so the relative error is one of the best ones to measure, but any one of those is valid. And the approximate error, I mean. And you can take them relatively, right? So remember, the relative approximate error, current iteration minus previous iteration over current iteration, right? And the same thing here. This is measuring how well your solution approximates the system of equations b minus ax, right? So you're measuring, does my solution satisfy the governing equations? And you divide it by the right-hand side to get a relative measure. That's a little harder to compute in practice. So I always prefer this one. And most linear solvers that you find out there, you can specify which measure you want. Usually they default to this one. Okay? That's what I have to say about that. Then you keep iterating until your error, however you define it, any one of those, is below a certain tolerance. Always go for relative error. Okay? Always go for relative error because it gives you a sense of scale. Okay, if you're dealing with a system of temperatures where temperatures are on the range of 1,000 to 5,000 kelvins, then an error of 10 kelvins is insignificant, right? So a relative error will allow you to capture that sense, right? So that's super important. However, just be clear, okay? Be clear about it. Now, in your homework assignment, be clear in the sense like this is the error that my solver does or measures. In your assignment, I made the iterative solver question a bonus question. Because in my mind, iterative solvers are sort of like additional material if you are interested in learning more and getting more involved with this stuff. So it's a bonus problem, right? So you don't have to memorize or kind of implement any of this. And I provided you actually with the implementations for the Jacobi and another solver called Gauss-Seidel. Yes? Yes, but the questions will be, describe how iterative solvers work, right? Start with the gas, refine it. Or for example, how would you measure the error in an iterative solver? You would say, I will take the solution for each variable, and together I'll build a vector and take the norm of that vector, right? That's the extent to which you're responsible for iterative solvers. I don't ask you about code, but I will ask you, how do they operate? For example, like, are they approximate or exact, et cetera, okay? So good question. Again, for those who are interested, this is pseudo-exact code for Jacobi, for example, and you'll have access to that in the Python file that I put in your homework assignment. I want to talk about one more solver before we start on nonlinear solvers. You will notice, if you do the bonus problem, you will notice that the Jacobi solver is kind of slow. And if you remember how the Jacobi operated, you go equation 1, you solve equation 1 for variable 1, equation 2 for variable 2, and so on. But the guesses that you use in all subsequent equations are the old guesses rather than the most recent ones. So if you solve equation 1 for x1, why not use this new x1 in the equation, in the second equation? And when you solve equation 2 for x2, take the new x1 and the new x2 and use them in the equation for x3, and so on. Jacobi solver doesn't do that. Jacobi solver uses only the previous guesses. And it keeps everything you solve for x1, x2, x3, and so on, using the old guesses, and then you take those and use them for the next step. Well, the Gauss-Seidel iterative solver says, no, let's just use the most recent information that we have, not the old information. And just doing that doubles your convergence rate. If you do the bonus problem, there's a question where I ask you, show the convergence rate between, study the convergence rate between Jacobi and Gauss-Seidel, and you will see that you will double, you will get there in half the number of iterations. And it's a very simple change. If you look at the Jacobi equation, again, don't get too involved in that. Just think about this as new estimate is equal to old estimate plus something. Okay, but this thing is always using the old values, k, the values at iteration k. With Gauss-Seidel, as you go through each equation, the new iteration uses the old value plus the most recent, whatever is available to you. Not just the old ones, whatever is available, just use it. Intuitively, that should make sense, right? Because you're just improving. You're just using the most recent information everywhere. And just by doing that, you double your number of iterations. Okay, I'm not going to go through this example. Again, this is just more to show you that, hey, these things work. And you have a lot of additional material at the end. For those who are interested, there's over 100 slides of additional material for how to do more advanced iterative solvers, how to do sparse solvers in Python, sparse matrix storage, etc. You might not need them now, but in a few years, you're like, oh, yeah, I remember doing this. You pull up the slides, come and talk, come and chat with me in the office. And it's a lot of fun. Anyway, but for those who want a little bit more of a challenge. Again, this additional material you're not responsible for at all on your exams. In every set of slides, there's additional material. You're not responsible for those, for the exam. This is more for you. If you are curious, if you want an additional challenge, and I'm happy to talk with you about those off hours. Okay, this completes linear solvers. So right now, if you want to assess where you're at, we looked at error. That we understand now that there's error in everything we compute. Round-off error is inevitable whenever you're crunching numbers. Truncation error is the error when we approximate full mathematical formulas because we want to put them on computers. We cannot add an infinite number of terms. You learned a very valuable tool when solving systems of equations, linalgebra.solve, or the A inverse. That is going to be your go-to tool whenever you see a system of equations. This is your go-to tool to solve it in all of your courses, and you're going to see that. So when you go next year to do mass transfer, you are expected to know how to solve a system of equations. If you forgot that, come back to these slides. Right now, if you cannot put a matrix, write a matrix just using these brackets and solve it with Python, you better do that as soon as possible because we're going to be doing linear solvers all the way through the end of the semester. That's why I teach it in the beginning. Okay, it's going to show up everywhere in interpolation, in regression, in ODEs, even in nonlinear solvers. Okay? All right, so we've learned this so far. This is the unit on solving equations. So we solved algebraic equations linear. Now we're going to talk about nonlinear equations. All right, so we will start with the chapter on nonlinear solvers. Learning objectives, just to help me also stay faithful to what I need to teach. You'll learn how to define a nonlinear equation. You'll learn to define what is meant by solving the equation f of x equals 0. What do we mean visually and verbally when we say solve an equation f of x equals 0? Define and write down the residual form of an equation. New, very simple idea that we'll introduce in this chapter. Define what is meant by the root of an equation. Define closed and open domain methods for solving nonlinear equations. We will create Python code that computes one or more roots of a nonlinear equation using built-in tools in Python. You see what I'm trying to do here? I'm trying to give you existing tools, black boxes, that you will most likely only use those in your career. But because you are engineers, we will dig in a little bit under the hood so that we know what goes inside the method. Okay, so that's beyond what just a technician would do, is just use fsolve or linalgebra.solve. How it works in the back end, we don't know. No, you need to know a little bit of what goes on under the hood, okay? Because you might be a creator of those tools in the future, okay? We will calculate the roots of an equation using Newton's method by hand, so we will learn what goes behind Python's built-in tool. We will also implement our own nonlinear solver for a single nonlinear equation. We'll identify a system of nonlinear equations, and I'll give you an example. That heat transfer problem example, we'll turn it into 1,000 nonlinear equations or 1,000,000 nonlinear equations. And that's quite complicated, but very interesting to do. We will interpret what we mean by the roots of a system of equations. And if we have time, or kind of more like, we probably will not have time for sure, we'll do these things in red. They are definitely covered in additional material, all right? And I don't have a story for you at the beginning, but I have a little video clip for you like halfway through from a movie where they use nonlinear solvers correctly. But we will start with an example. Okay, so I will have to narrate this example rather than listening to a film. So let's say in your municipality, in your city, and some flooding occurred and 26,000 gallons, or about 98.4 cubic meters of water leaked into a pipe under construction. So these large pipes, you've seen them being installed. You can walk in them, etc. The pipe has a length of 15 meters and a radius of 4 meters, so diameter 8 meters. And the question is to find if a maintenance person who's 5 feet 7 tall, or about 1.7 meters, can walk through the pipe to investigate the damage without being submerged in water. So the question is like, is it safe to go in the water? And suppose like, you cannot peek in, or like you don't know where the bottom is, and you just don't want to just jump in and drown, right? So the question is it safe to go in there? All right, so it turns out that there's a formula for, interestingly, someone studied this because it's like an important problem in civil engineering. And if water were to spill into one of those large pipes, there's a formula that relates the volume to the length, radius, and the height of the water in the pipe. So in that formula, you have the volume V, which is kind of given to us. We know how much water went into the pipe. We have the length L of the pipe. We have the radius, right? But we do not have H. So if we were to try to figure out whether this person, this maintenance person, can go in the water, we need to find H, given V, L, and the radius, which we know the radius is 4 meters, V is 98.4, and L is 15 meters. Then, we just need to compute H. Okay, so here's my question to you. Give me H. What is H? I gave you a formula, right? Can you solve for H? Tell me. Talk to each other. This is the stuff you will be dealing with as engineers. Pardon me? What is that? Symbol lab? Well, try it. Try it. So with what you know, with the tools that you know, just simple basic calculus, can you find H? No. So I got to know. I don't even know if that's possible, because you have an inverse function for the cosine, you have a square root, and you have a quadratic, right? Well, no, the r squared is fine. So you have an inverse function, and you have a square root and a quadratic under the square root, right? So okay, so some people are saying no. Some people are saying maybe if you have enough time, you could probably solve it. Or is it a no? Can you solve it?
Use Excel goal seek.
Excel what?
Goal seek.
Okay, well, I've said analytically, right? Can you solve this analytically, right? So I'm trying to make a point, okay? The point here is that with the tools that you have, this is not like taking, x squared equals 3 and then x equal the square root of 3, right? It's not as simple as that. The point is that there are equations like this one and systems of equations like that one that are so complicated that you cannot just simply extract one variable out of them by doing simple algebraic manipulation, right? Maybe next year, maybe I have to pick an even more complex equation so that everyone says, no, we cannot solve this. We'll see, maybe for next year. Okay, so we know how to solve a single linear equation, obviously. And in this class, we learned numerical tools to solve a system of equations. In this chapter, you will learn how to solve single nonlinear equations, like this one or the one on the pipe. We'll come back to that and solve it together. And systems of nonlinear equations. So, for that pipe problem, you might have another equation for the volume or for the radius that's dependent on something else, right? And that is nonlinear too, and they're all coupled to each other. You cannot solve one of them without solving the other, and they're both nonlinear. But what is a nonlinear equation or function, right? So it's always been like a fleeting definition. The way I like to define it very simply is a nonlinear equation is an equation where the variable of interest, so be careful, be attentive to that word, the variable of interest appears nonlinearly. And by that, I mean two things. Either it is being squared or cubed or to some power, or under some transcendental function like sine, cosine, logarithm. Now, if you go back and look at the equation I showed for the pipe, you have V and you have R and you have H. The volume shows up linearly because it's not squared, it's not under any transcendental function or anything like that. But H shows up nonlinearly. So here's another example. In this equation, you have four parameters, A, R, Q, and H. Okay? So take a minute and think about how each one of those parameters or variables shows up, linearly or nonlinearly. Remember, for a variable to be nonlinear, to show up nonlinearly, it has to either be squared, cubed, to the power 4, etc., or under a transcendental function. Sine, cosine, square root, exponential. So does A show up linearly? Does R show up linearly? Does H? Does Q? So what do you think? Make a list. Like this is a classic exam question, okay? This is a classic exam question. You will be asked that question, this one. It's a nice one, right? Like that usually motivates everyone when I say it's an exam question. Everything is an exam question. All right, let's start with A. Does A show up linearly? No. Okay, why? We got A squared, and we have the square root of A, right? So it shows up non-linearly. What about R? Linear, that's correct. It's multiplied by A squared, but R itself doesn't show up non-linearly, okay? It's just scaled by A squared in a linear fashion. Same thing by Q cosine H multiplies R. R shows up linearly. What about H? Okay, nonlinear. Which term is the culprit? The cosine term, right? Cosine term. And finally, Q, linear. Okay, great, you got it. Okay, so R and Q, they both appear linearly. A and H appear nonlinearly. Now, is this a linear equation or nonlinear equation? Well, you have to tell me, like, from the perspective of which variable. If the only unknown here is R, then this is a linear equation in R. So that's a stronger statement when you identify your variable of interest and say that variable shows up linearly or non-linearly. Okay, so I hope now that kind of clarifies, because if it clarifies the difference between linear and non-linear in just one shot and one swoop. Okay. All right. So next, what do we mean when we solve f of x equals 0? You've done that, right? Solve x squared minus 3 equals 0, right? You've had problems like that. So what do we mean by that? Okay. Here's some function shown in blue. That's my f of x. So on the x-axis, I have the x values. They're the independent variables. I choose them independently. And the y-axis is the response, is the f of x. Each value on this blue curve depends on the independently chosen value of x. When we say find f of x equals 0, we specifically mean finding the intersection of that curve, of that function, with the x-axis, or specifically with the line y equals 0. So if you think about this function, this equation as y equal f of x and y equals 0, this y equals 0 defines this horizontal line, okay, that black line. When you say f of x equals 0, you're saying I want to take the intersection of f of x, y equal f of x, with the line y equals 0. When I intersect them, there are some points shown in red. Those are the intersection points. And when we say solve for f of x equals 0, we mean to find those points where f of x intersects with the line y equals 0. Very specific. It's a very specific definition. So solving an equation, f of x equals 0, means finding the values of x that make f of x equals 0. Those values of x are called the roots of the equation. Okay? And they are also referred to as the zeros of the equation. The zeros that make the equation 0. Visually, it's very nice to interpret it this way. Unfortunately, it's hard to do a visual interpretation when you go to functions of many variables. F of x, y, z, q, etc. It becomes a little bit more complicated. But in simple 1D situations like this, this is the best way to visualize a function. Okay, so I'm going to guide you through a few exercises now to elevate a little bit this definition of f of x equals 0. So we will start with this curve. Visually, this blue line is some function. Okay, so locate the root of that blue curve. And you see so when I say locate the root of that blue curve, means saying that blue curve equals 0. Where is it equal to 0? Where is that root? Just kind of pinpoint it approximately, you know. Okay, so could you point your finger to it? It's over there. Okay. So it's simply that intersection of the blue curve and the line y equals 0. Okay, so just pinpoint it. Okay, you got it. Okay, great. Now let's take another function. The blue curve now is given by this f of x. It's called f of x. Visually locate the root of f of x equal 10, not equal 0. So I change 0 now, I put 10 over there. So now you're finding the intersection with what? Yeah. With the intersection of the blue curve with what line? With y equal 10? Yeah. Yeah. So which line are we intersecting the blue curve with? Y equals 10. Okay, good. Okay, so the root of f of x equal alpha is the point of intersection of y equal f of x and the horizontal line y equal alpha. Okay, good. There's no genius over here. Okay, so let's move this to the bottom. Remember this same function, f of x equal 10, has a root at 6.75. Now I'm going to take that same red function and redefine it into another function, f of x minus 10. It's the same function, looks the same, except it's shifted down, right? So now, what is the root of f of x minus 10? Equals 0. Where is it visually located? And what is the value given what you know about the It's the same function. So is there a difference between f of x equal 10 and f of x minus 10 equals 0? Is there a difference? Okay, so what's the root? 6.75. There's no difference between f of x equal 10 and f of x minus 10 equals 0. We just rearrange terms. We just move the right hand, everything to the left-hand side. Agreed? So look at it. It's the same root. Exactly the same root. Now this is important because we need to talk in a unified language when we talk about roots of functions. Is it the root of the function equal to 0 or the root of the function equal to something else? I want everything to mean root of the function when whatever rearrangement of that function is equal to 0. That's just like one standard way to communicate about nonlinear functions. So the value of the root did not change. Both f of x equal 10 or r of x equal f of x minus 10 equals 0 have the same root. When you move everything to the left-hand side and set it equal to 0, we call that the residual form of the function. Very simple. Whenever you see a nonlinear equation, move everything to the left-hand side. Put it in residual form. Okay? The root of f of x equal alpha is the same as the root of r of x equals 0, where r of x is f of x minus alpha. We just redefined it. And r of x is the residual form of the equation. It's just a way for all of us to communicate moving forward to say, find the residual when it's equal to 0. Find the root of the residual. It means when r of x is equal to 0. So I don't have to worry about f of x equal 10 or f of x minus 10 equals 0. Just the residual, find the root of the residual function. I'm always meaning that that residual is equal to 0. Intersection with the axis y equals 0. Okay, so here's some exercises. Now write log x plus cosine x squared equal 3 in residual form. Write r of x, redefine that equation. Just move everything to the left-hand side. I know they look simple, these exercises. They look very simple until you get to the exam. Just do them, please. Please try to do them. Humor me. Just write them down. Okay? Get used to writing the residual form. Move everything to the left-hand side. All right, let's see. Do we have any volunteers from the back? I can't even read your names. Andy. All right, go ahead.
The natural log of x plus cosine of x squared x minus 3 equals 0.
Yes, exactly, right? Now, you should call all of that, that's your new function. Okay, that's r of x. And you always call that r of x, r for residual. That's how we are going to communicate about this. When I tell you residual form, I'm meaning taking everything, putting it on the left-hand side, that's your residual form. Okay? All right, so now we're going to go back to that pipe problem. V equal L into r squared inverse cosine r minus h over r, et cetera, et cetera. We are given V, L, and R, so we're looking for h. H is our variable of interest. So now write this in residual form. So we're interested in finding h. So now write this in residual form. Now you might ask, is it okay to move things to the right-hand side? Of course. Left-hand side, right-hand side, doesn't matter. There's absolutely no effect on the procedure. It's in your mind. right? Who's got a residual form for me?
L r squared inverse cosine of r minus h over r minus h squared root 2rh minus h squared, all minus b.
Okay. That is the residual form. Or, so your colleague moved everything to the right-hand side, or you can move everything to the left-hand side, doesn't matter. That entire statement here, you call that residual r of x. In this case, r of h, because our variable of interest is the height. We're trying to find h. That's our unknown, right? And then finding the root of the residual means finding r of h equals 0, finding the values of h that make the residual function equal to 0. Okay? Good? All right, so now let's see how we can solve this in Python. There's a very neat library in Python called SciPy. You probably heard of it, scientific Python. So far you've heard of NumPy. You also probably know it before this class, but some of you might have learned just in this class. So numerical Python, NumPy. There's another library called sister library, but it does different things, called scientific Python. So scientific Python focuses more on algorithms and routines for like complex equations, differential equations, etc. And it works really, really well with NumPy. So it's like they're made by the same developer. But it has different purposes, SciPy. So NumPy gives us the ability to operate on arrays and matrices, and we use linear algebra solve. We compute also norms, etc. with NumPy, but that's about it for NumPy. Moving on, for the algorithms that we are going to be needing, we're going to be relying more on SciPy, okay, using NumPy arrays. So SciPy, just like NumPy, has a sub-module called linear algebra and so on. SciPy has a bunch of sub-modules. One of them is optimize. Okay? We'll try to understand why they call it optimize, why nonlinear solvers are in the optimize sub-module. But know for a fact that SciPy.optimize offers many nonlinear solvers, the most versatile, most robust of all of those, and the one that will cover 99% of your problems in your career is called fsolve. That's like if you've used MATLAB, if you come from a MATLAB background, that's also what it's called in MATLAB. The way you grab fsolve is simply say from scipy.optimize import fsolve. Rather than importing everything from SciPy and SciPy optimize and overloading your memory, just import the module that you're interested in. All right? Here's the function signature for fsolve. And you only need, right now, you only need the first two parameters. Nothing else. There's a bunch of, probably 10 other parameters. You don't need any of those. Okay? So fsolve will require a minimum of 2 arguments. The first argument is a definition of your Python routine for the residual function, or a Pythonic version of your residual function. Remember when we went back to when we did the derivatives and we said we wanted to compute the first derivative for any function, and you were like, okay, how do you do that? Like, just give it the name of that function, of that Python routine, just the name. That's technically called a handle to that Python routine. So here's how it goes. You define your residual function by hand. You go in Python and write a subroutine that computes that residual function. So v minus L, r squared, et cetera, okay? And then you pass the name of that subroutine as the first argument to fsolve. But there's a very important condition in that your residual subroutine, the first argument of that subroutine, it needs to have at least one argument, and that argument needs to be that variable of interest that you're solving for. Otherwise, it will not work. So in our Py problem, we will go ahead and define a subroutine for v minus L, etc. And the argument for that subroutine is going to be h, because we're trying to solve for h. Everything else is given. We can define it, v, L, and r. We'll define those in that subroutine. But then h is what we're looking for. And that first argument cannot be anything else. It has to be that, it has to refer to that unknown of interest. Why is that important? Because there will be residual functions that depend on 10 other parameters that you may want to pass through the nonlinear solver. But the first argument needs to always refer to the unknown. Okay? You'll see it once we implement it by hand. There's one other important argument, and it might not be obvious right now until we get under the hood of what's going on with fsolve, is this x0, and that's an initial guess. That is your best guess for where the root is of that residual function. Now, the fact that I mentioned an initial guess should immediately indicate in your mind that fsolve is probably an iterative method. It starts with an initial guess and works on improving it, just like the Jacobi iterative solver worked. And indeed, that's exactly the case. All right? So once we go under the hood, you'll see why we need an initial guess. Okay? And so, for example, if your residual is looking for some variable x or h or whatever, you just define it like that. Define my residual, and then you implement it, you return a value, and you're good to go. It just works like magic. Okay? And you simply call it like that. You give it the name of your residual function, and with an initial guess. Okay, so grab your Jupyter notebooks, and let's solve this pipe problem by hand, and think about, solve it in Python, and think about what we're going to do with the initial guess, okay? So I'll move this, while you get your Jupyter notebooks up and running, I'll move the slides to the other window. Okay, grab a new Jupyter notebook. Or your VS Code, or whatever you're doing your Jupyter notebooks in. Okay, window. All right. So let's zoom in. All right, so nonlinear solver example, pipe flooding problem. Okay, so that's in class. We're doing that in class. All right. So I will get my usual boilerplate. We will probably need NumPy, because I would like to at least plot the residual function. So we'll talk about that in a second. So import NumPy as MP, okay, and the magic matplotlib, matplotlib inline, and then config inline, line backend dot figure formats equal SVG, and import matplotlib.pyplot as PLT. Okay, so that's my boilerplate, and we will need fsolve. So I'm just going to go ahead and import it here from scipy.optimize import fsolve. Come on. Giving me that star over there. Okay, good. Okay, so this is, this is the code over here. Let's shrink it a little bit, like this. You guys in the back can see? Good? Great. All right, so this is my residual function, and it could be either you take everything to the left-hand side or to the right-hand side. Okay. So that's our residual function. We will assume that V, L, and R are given to us and they're hard-coded. okay, inside that function. So we're not passing them as parameters. Later, we will pass them as an optional parameter. Okay? But now I just want you to focus on the variable of interest, which is h. So let's go ahead and say define pipe residual, and that is going to be a function of h, okay, at a minimum. Because the fsolve, what it's going to do, it's going to try it's going to keep passing h values to the residual function until it finds the root. So that's why we need that argument of that variable of interest, right? Okay, so we have v is equal 98.4, that's cubic meters, and r, the radius, which was 4 meters, oops, and L was 15 meters. And finally, my residual, we'll store it in a variable called result, is V minus L times, open parentheses, R squared times, now what is inverse cosine? It's R cosine. Okay, you can bring that from the math library or the NumPy library. We'll just use NumPy. np.arc cosine. Why do I recommend you use the NumPy library? Because eventually we will be dealing with systems of nonlinear equations, and you will be passing an array of variables. So only NumPy.arc cosine will take a NumPy array, not the math arc cosine or any other arc cosine. Okay, that's why I like to use the NumPy library for these things. So arc cosine of r minus h over r. Okay, so that closes parentheses. Perfect. Minus, let's expand this a little bit. Okay. Minus r minus h times mp dot square root, okay, so open parentheses, close parentheses, of 2 times r times h minus h squared. Oops. Agreed, and then one final parentheses there, right? So they should be balanced. Okay, green, nope. This one is not balanced. Okay, yeah, there you go. Okay? And then return result. Okay. This is a standalone Python routine. You could plot it, you could pass numbers to it, etc. Okay. In fact, let's go and plot it. Why not? Let's see how that residual function behaves. Okay? So let's create a linspace. This is mp.linspace from, let's say from 0 to 8, right? Because h cannot be more than 8 because the radius is 4, the diameter is 8, right? So the height of the water can be no more than 8. Only goes from 0 to 8. So it makes sense to plot that residual, okay, between 0 and 8. And simply plt.plot x and pipe residual x. All right, so before I plot it, what should we expect here? Remember, this is the residual function, some weird function, v minus a bunch of things. Doesn't necessarily have to have a physical meaning, but there's a few points on that plot that are going to matter a lot. And those points are when that residual function intersects the x-axis or the y=0 axis. Those are going to be our roots. So those are the points that we are really interested in. Does the residual function have to be positive? Negative? Doesn't matter. In fact, it has to go from positive to negative if there's a solution, because that's the only way you can get a root. is for the function to change sign. Otherwise, you will never cross the x-axis, right? Does that make sense? If a function is always positive or always negative, it means it never crosses the x-axis. It means it doesn't have a root. So I do expect that this function intersects the x-axis if it has a solution. So let's see. All right. Oh, perfect. OK, so there's positive and negative values. So it tells me it does have a root. Let's add a grid, plt.grid. All right. Well, luckily, the grid intersects, shows the y equals 0 axis. And look at that. It looks like there is a root. So let's zoom out a little bit here or just expand this guy. OK. So this is like a really important thing to do, especially for one-dimensional functions. In 2D, 3D is very difficult to do. But for 1D functions, if you plot the residual function, it just gives you a very clean idea of where your roots might be located, which will therefore help you in your selection of the initial guess. Okay, so we can plot the y equals 0 axis. And you can do this by doing plt.plot, plt.ax h line, a horizontal line, a horizontal axis line. That's what ax h line means. And you could say I want this to be at y equals 0 and give it a color. Let's say black, K for black. OK, there you go. Okay. So this is our intersection of the function with the y equals 0 axis. And notice the function starts at some value. I don't care what that value is. It's a residual function, whatever it means. All I care about is if it crosses the x-axis and how many times. Here, it crosses the x-axis once, so it does have a solution. And the root is somewhere between 1 and 2. And it seems like it's almost like 1.6. Now, the person's height is 1.7. So like it's really cutting it close. But by how much, we don't know until we actually find that root numerically. OK? So let's go ahead and do it. So we're going to call fsolve. If you want to see the function signature, you go in the parentheses and press, and it gives you that function signature. You see it has a bunch of other options. You only care about the first two. Next, we will learn about the third one. But it explains the function call, the residual function, the initial estimate of the root. So in our case, we just need to give it the name of our residual, which is pipe residual, just the name. Just the name. And then some x0. x0 equal, what do you think our initial guess should be? 1.5. OK. Oh, look at that. It converged pretty quickly to a value of 1.505, 6, etc. So that tells us that for V, L, and R that were given to us, 98.4, 15 meters length, 4 meters in radius, the height of the water is going to be 1.5 meters. So that person has about 20 centimeters, so they're going to be submerged to this level. It's going to be annoying.
Why does it not like you if you give it like 0 or negative?
Because it's not always guaranteed to converge. So that's going to be my next discussion. So first of all, it doesn't make sense to give it a negative value because it becomes outside the scope. Okay. Now, when you gave it 0, what happened? Probably you got stuck in a local minimum or a local maximum, which is the Achilles heel of these methods. We will study this a little bit later once we go under the hood. Okay. But this is just to get us moving. Yes, Michaela. The initial gas sets the initial point where the method is going to try to improve. It starts from somewhere. It's a guess of the root. It starts from that point and improves it. Think about the Jacobi solver. We started with some random initial guess. Then we used the equation and kept refining the guess. The same thing is happening here. We will learn about that after we finish this example. We'll get under the hood to understand what's going on behind the scenes and why we need an initial guess. Initial guess is very important. because like your colleague was just asking me, if you choose a bad initial guess, you might never converge. So what guess did you choose, Davin? Or 0, right? Let's choose 0. Oh, see? A bad initial guess will get you to not converge. Now, how do you know if it's good or bad? Well, you really kind of don't know, especially when you go to higher dimensions. In 1D cases, it's pretty obvious. We know the root is between 1 and 2, and really, if I could choose maybe 0, if I had chosen 0.1, I would converge. If I chose 4, I would converge. Okay? But there's a problem going on here at 8 and at 0, okay, that causes this method not to converge. We will study that, again, I promise you, once we go under the hood. It gets stuck in a local minimum or a local maximum. But we will demonstrate that later. But for now, here's the guideline. For 1D problems, it's easy. Plot the residual and pick an initial guess close to that root. Now, you can visually see the root. Pick as close as you can. The method will get you the most accurate number that you cannot get visually. For 2D cases, sometimes you can plot them and get an idea of where the root is, but you're out of luck there. You have to start studying the system itself, right? Or maybe exploring the space by trying different combinations of initial guesses. So that's the worst situation that you get stuck in. Now, fortunately, for very large systems of nonlinear equations, again, like the interest in these is when you go to nonlinear regression, for example, or when you go to nonlinear partial differential equations, where you have thousands of these equations. Guess what? The initial guess in those cases is known from the initial state of the solution. You advance the solution a little bit, then you take that as your new initial guess and advance it some more and advance it some more, and you'll always have a good description of your initial guess for the nonlinear solver. It doesn't mean it's bulletproof, okay? But in those cases, your physical judgment comes into play. So for example, you could say, well, you know what? I'm mixing these two gases. There's no way the density is going to be 10,000 or negative, right? So you pick a value that is physically relevant. For our intents and purposes here, I will give you the initial guess, okay? And you can proceed to use it, and you'll get an answer. But as you go into more unknown territory, you will have other information about your system that will help you choose your initial guess. Yes?
So like, would you have the same thing if there was multiple, like if it crossed it multiple times?
Yes. So when you have multiple roots, there's no guarantee to which root is going to converge. So when you have a sine function, for example, or a polynomial that crosses the axis multiple times, you might have multiple roots. If you have to choose the one that's closest to your root, so that you converge to that root. Yeah.
So when you on like a calculator, when you have to choose like the upper and lower bounds, is that doing the same thing?
Yes. So that's called a closed domain method, a bracketing method, which is a method that I don't teach anymore, but it's given in the appendix of these slides. So what your colleague is saying, when you're using a fancy calculator to find the root of a function, some of those calculators, they ask you for a bracket of the root. That bracket is essentially guaranteed to converge you to the root. You give the left side of the function, the right side of the function around the root, and what it does, it keeps cutting the interval in half and evaluating the function until it gets to f equals 0. So it's like a brute force approach. You take the ends, cut it in half, and then take the ends, cut it in half, until you get to f of x equals 0. This method, and again, you're kind of getting ahead of me. This method is called an open domain method. You only need one value for the guess, not two values. Because to bracket the root is impossible to do in 3D or higher dimensional spaces, right? Whereas in my case, for example, when I take the heat transfer problem, which I promise we will do when we get to differential equations, guess what my initial guess is going to be? The average temperature. So we will be solving for a temperature that shows up nonlinearly with radiation and all sorts of things. My initial guess will be the average temperature in the problem, and it always converges. Because that's kind of the one that physically makes sense in that problem, right? So you will be guided by the physics, all right? So it's the hardest problems are the ones where you just get in math equation and you're like, there's no context. Solve cosine x plus log x equal 3. I'm like, okay, where does this come from? Where do I choose an initial guess, right? At least in engineering, you have a physical setting, right, to inspire from, to be able to use as your initial guesses. All right. Now, functions with arguments. If the residual function requires one or more arguments in addition to the independent variable, okay, so if we were to go back to this problem, and then Sandy City calls you and says, oh, we have a flood, but our pipes are 5 meters in radius, and there's like 124 cubic meters of water spilled, and our pipe length is 11 meters, right? So you saw I had to go and change the values inside that function, okay, then evaluate it, run it again. Now that moved the root to almost 2, and then, all right, indeed, the root is at 2 in that case, and the person cannot walk in that pipe. But the point is, we had to go in and hack those values in, kind of put them in manually. Well, you might say, if you're a good programmer, instead of defining the residual like this, why not give it the arguments v, l, and r, so that we have a more general description of the residual function? Because as a matter of fact, v, l, and r, they still show up as parameters, right? They're symbols in that equation. So we can change them. So why not pass them as argument? So let's define another residual function, pipe residual with args, with arguments. Okay? And again, the result is the same. But in this case, I'm passing more than just the variable of interest. So the question is, how the heck do you pass this in fsolve? So if I were to go here, pipe residual with args, I'll give you a second to type that. Just simply put in the arguments v, l, and r. And now this function over here, this result, is going to inherit the values h, v, l, and r from the arguments here. So it will take those and plug them in here and returns a result. Okay, so now if you try to pass to fsolve, it's going to barf at you. So fsolve, pipe residual with args, x0 equal 4. It's going to throw an error. Oh, yeah, some error. What is it? You go to the bottom. Pipe residual with args is missing 3 required arguments, v, l, and r. So it doesn't know what they are. Turns out that fsolve allows you to pass those arguments directly from fsolve. You might not see the value in that because, well, you say we could just go and change v, l, and r over there. And you're right in this case. But oftentimes, that pipe residual is outside your scope, is a function that you don't see, is in a library that's hidden. And your fsolve is spanning the space. Maybe you're looking at all the possible solutions for all combinations of v, l, and r. So you do a loop, and you call fsolve in the spot with different values of v, l, and r. You don't have to go and hard code or pass arrays for v, l, and r. So the way you do this is simple. Oops. Okay. You define your residual with your additional arguments, a, b, c, d, e, f, g, whatever. So those are your additional arguments. But then in the fsolve function, so we have the handle to the residual routine, the initial guess. Your third positional argument is you pass the arguments here to that function. So what fsolve does, it will call my residual, will put x0 here, and will put abc after it automatically, or a, b, c, d, e, f, g, whatever. Okay? Just a little neat trick so that you can have cleaner programming. All right? So here's how I would fix this. I would pass args equal, and let's say I define those as v, l, and r. So, 122.4 and whatever, 10 meters for the pipe length, or what was it? 11 meters and 5. 11 and 5. And now it works. Okay? What was it? 124.4. Okay. Indeed. It's the same exact root as the other one, except now I am passing those additional arguments, V, L, and R, as part of fsolve. I don't ever have to revisit that residual subroutine. Okay?
You might have talked about this already, but does it pass, or does it return H because H is defined first in the function?
You always have to yes, you always have to define H as your unknown, right? Yeah. So the value that is returned by fsolve is the value of H that makes the residual function equal 0 with those arguments. Okay? Yeah. Yes.
Is it possible to define H but instead leave something else unsolved? You just switch the arguments in your initial guess.
No. The first argument in the residual function has to be the one that you're solving for. Yeah. Yeah, you would have to define another subroutine. So that's a great question, because so what your colleague is saying, well, now what if I have H, but I want to find the radius of the pipe, right? You have to redefine your residual function, okay? Because it has different meanings. H has a meaning, R has a meaning, right? Okay. Let's resume. We're almost done. Nonlinear solvers. We'll wait for your. So we started maybe 30 seconds earlier. I know you're very punctual. So nonlinear solvers generally fall into two categories. Just like linear solvers, you have direct and iterative. Nonlinear solvers fall into two categories: closed domain methods and open domain methods. Closed domain methods are very simple and unbelievably robust, and they're based on the idea of bracketing the root. You say, I have a root somewhere between these 2 points. Those 2 points, treat those 2 points as your bracket, then cut that interval in half. And then check again, is the root to the left side of this half or the right side? Then take that half and cut it in half again, and cut it in half, and so on, until you converge to that root. They're super robust. If you have a bracket that brackets a root, you are guaranteed to converge. Now, they are not practical because they will only work on one-dimensional functions. We could design them for 2D and higher dimensions. We will have like a hypercube, but they get unbelievably complex because then you would have to visualize your residual function and try to guess where the root is. They become impractical. Because in practice, you want to run your code that is solving a system of nonlinear equations. You don't want to interrupt it and visualize where the root is and think about it, right? You just want a method that automatically figures out where the root is. So this is where open domain methods come from. And the naming of closed domain is because you're closing in on the root. You've enclosed it with a bracket. Open domain methods, on the other hand, start with just one initial guess. Just give me 1 point, and I'll figure out my way to get to the root. And you essentially trace where the function is headed towards 0. You follow its descent or ascent, okay, to get to the 0 of that function. If you're negative, you're going to go up. If you're positive, you're going to go negative slope so that you get to the root. Unfortunately, so they are very efficient, but they're not as robust as closed domain methods. Because unfortunately, they're not guaranteed to converge, as we've demonstrated a second ago. Luckily, with good intuition about the system or with partial differential equations, you always have a reasonable starting point for the guess, and almost always you are guaranteed to converge to a root. If you don't converge to a root, you have other issues usually in your problem configuration than the initial guess. Your equations might be implemented incorrectly, for example, rather than the initial guess itself. So I'm speaking from practice. This year, we will only cover open domain methods, specifically the Newton-Raphson method. So the Newton-Raphson method is also known as Newton's method, okay? And have you seen the movie 21? You've seen it? So okay. Do you remember that discussion with Kevin Spacey about? Okay, so let me remind you of that. Now YouTube is gonna spot this as what, copyright infringement or something. It's like, come on, this is for illustrative purposes. All right, so let's see if you can hear me okay. You can hear okay. So this is a clip from the film 21. Probably it's still on Netflix. It's about games of chance and calculating numbers, etc., and turns into a drama and whatnot. Okay, let's see.
All right. Now, who can explain Newton's method and how you use it?
You can use it to solve nonlinear equations.
That's impressive. That's really good. I'm very impressed by that, especially since my class is called Nonlinear Equations. All right, now somebody tell me something I don't already know. Anyone? Bueller. Anyone? Bueller.
Newton stole it.
I'm sorry?
Newton stole it. Joseph Raphson published the same method 50 years earlier. If the start value is too far removed from true zero, then it fails.
I'm sorry, what's your name?
Ben Campbell.
Ben. So Ben Campbell suggests that Joseph Raphson was the original author of this method. Well, if that's the case, then why didn't he get any credit? Well, for one thing, Newton had a better publicist. And for another, after 1700, we know very little about Raphson.
Okay, so that's to show that this is like, you know, and they use it in the right context over here, unlike most kind of math in the movies. But the point is that every time I see something like this in a movie, like The Nerd Turns On, I start telling everyone, hey, we know I teach this method to my students and all of that, and they're like, shut up, what are you talking about? Okay, all right. So that's the method we are going to learn. It's called the Newton-Raphson method, and indeed, Raphson published it a little earlier, and I guess, I'm kind of running out of time. Well, we'll let you go. We'll come back on Thursday. We'll start from this spot, okay? And we'll learn about the Newton-Raphson method.